Christian, you know I don't care.
All right, let's open up to 246. I got it.
He's probably sweating.
I do not.
He's nasty
All right, we're going to kind of wrap up our second derivative test that we ended with yesterday. We have one more example to go over, and then we're going to dive into the last section of Unit 4, which means test coming up soon, okay? So I'm anticipating, I have the dates on the board. I'm thinking we're going to finish the last section tomorrow. Monday is going to be kind of a practice day. Tuesday is a free response day. No, wait. Yeah, Tuesday is a free response day. Wednesday, the 11th, we're going to have our partner quiz. And then Thursday, the 12th, is going to be your review day. Now, I don't know if we're in band in here. That's mostly my other AP. No. Okay. So they have a band field trip on the 12th, so they just be missing the review day. But the test seems like it's going to be over the weekend. So we're going to have one part on Friday and then the next part on the following Monday. Okay? So we're going to have our test in before break. Yeah.
The test is everything, like 4.1 and 4.4, right? What are we doing?
Let me get back to you on that, because we already tested on 4.1 and 4.2. I'll get back to you. Okay. If there is a question or two on the previous sections, I'll let you know how many. Okay, but my guess would be the majority of it is going to be 4.3 and 4.4. Okay. All right. So let's go ahead and take a look at number 2. We're going to try to locate the maxes and mins. But this time we're just going to practice using the second derivative test. It's an alternative way that we can find maxes and mins instead of having to go through kind of the sign chart method. And I do want to go over an example with you today that's not in your notes. So you might need to write it down on a separate sheet of paper if you want to have it handy with you. But I want to show you an example where the second derivative test is your only option to find maxes and mins or confirm a max and a min. All right, so let's start with 2. If you don't like the thetas, you can change them to x's. So we want to find any max or min for this function on this interval, and we're going to try the second derivative test. So can we kind of go through and brainstorm how this works? What do we need to try to find first, perhaps? Yeah.
We need to find critical points.
Critical points, and critical points come from
Where the first derivative is equal to
0
0.
or undefined. Okay, so we've got to find the first derivative, set it equal to 0, think about if it's undefined, solve for x. All right, so first derivative of 2 cosine. Negative 2 sine. Good. And we got to subtract the derivative of x, 1. All right, so looking at this derivative, okay, sine is a wave, if you think about it graphically, and there's no holes, there's no jumps, there's no asymptotes, nothing like that for sine. So there's no place where this would be undefined. So we're not going to get any critical points that way. So the only other option is for us to set it equal to 0 and solve for x. Now you may have to use your unit circle, okay, depending on how familiar you are with it. That's on page 10 if you have to flip. So we'll subtract the 1, divide the negative 2, so we'll be left with negative a half. On the unit circle, At which radian locations does sine have a value of -1/2? If sine's negative, can we figure out at least which quadrants we're in?
3 and 4.
3 and 4, the bottom two, because sine is y. Okay, so 3 and 4. There we go, 7 pi over 6 and 11 pi over 6. Good. Okay, so these are our critical points. These are the possible maxes and mins. Okay, you have to test them. So what we did previously is we would use these in our sine chart, and you'd have to pick radian values in between these critical points, okay, and then test those. But let's try the second derivative test. Maybe it'll be a little bit quicker. So the second derivative test, first of all, involves finding the second derivative. So look at your first derivative, and we're going to go another round. The derivative of -2 sine, -2 cosine, and then we have to subtract the derivative of 1. 0, so you don't have to write it if you don't want to. All right, so here's our second derivative. How can we use that to see if these critical points are actually maxes and mins? Sometimes they might not be.
You have to plug them in and see if they're positive, negative, or 0.
There we go, positive, negatives, or 0. We want to see what the sign is, okay? So what's nice about the second derivative test is you're actually plugging in the critical points you know. If you were to do the sine chart, pluses or minuses, you would have to plug in other radian values. Like you would have to think of something between 7 pi over 6 and 11 pi over 6. Okay, so this one's a little bit more straightforward in my opinion because these are the numbers you're using. You don't have to think of new ones. All right, so unit circle, not something I require you to know, but if you were to plug in 7 pi over 6, what's the cosine value? There we go. So we have -2 times negative square root of 3 over 2. So this was the radian in the quadrant 3, and if the sine value was -1/2, then the cosine value would be the square root of 3 over 2. And since it's in quadrant 3, cosine is negative because it's an x coordinate. So if we multiply these together, negative times negative goes away, 2 divided by 2 goes away, so we're left with the square root of 3. All right, can we write a justification based off of that? F of 7 pi over 6 is a max or min? How'd you know it was a min?
Because f of x is concave up
Mm-hmm.
at 7 pi over 6, therefore it should be a minimum.
Right, so if the second derivative is positive, you are concave up at this spot, and since it was a critical point, a potential max or min, that clearly defines a minimum for this concave up picture. So f of pi over 6 is a min because the second derivative is positive. All right, let's test the other one. All right, so 11 pi over 6 is from quadrant 4. We have cosine values that are positive there. So this would just be a positive square root of 3 over 2. And the 2's would cancel, so we're left with negative square root of 3. So if the second derivative is negative, f of x is concave down, so the critical point must then be a max. So f of 11 pi over 6 is a max because the second derivative is negative. Do you see how that might be a little more straightforward or simple instead of using the sine chart? Okay, especially for trig ones, I think that might be a better option for us. All right. let's take a look at a case where this second derivative test is the only option you have. So if you just want to pay attention, that's fine. If you have a scratched piece of paper that you want to write this down, that's okay too. So I just thought of this question. Is the point 3, 1 a max, min, or neither if we know a derivative is given by this implicit equation? Remember doing these in 4.1 where we wrote dy over dx equals everything? Okay, so let's first try to see if this point is a critical point. Is it a potential max? Is it a potential min? How do you want to do that? How can we determine if it's a critical point? What do you think, Christian?
Nah, I don't got it.
You don't got it.
Top equal to 0?
That's where we'd have horizontal tangents. That's where we would have vertical tangents. Yeah?
Would you like to plug in the x and y into the thing and then set dy over dx equal to 0?
Well, if we're going to plug it in, we're going to see if it's true. Okay, so definition of critical point is where the first derivative is 0 or undefined. So if we're testing this point, we want to see if this specific point makes this derivative 0 or undefined. So let's check it out. We'll have 3 times 1 squared minus 3 over 3 plus 1 squared, 0 over 4, 0. So we know that this point is a critical point. So now it's a potential max or min. We got to test it though. So if you decided to use the sign chart, how would you want to set that up? Can we think about what the intervals would be? Notice how the x value of the point is 3. So maybe you'd want to go from negative infinity to 3 and then 3 to infinity. Okay, so that's one possibility you could do to test this. Pick a point between negative infinity and 3. 0. Then we plug it into the derivative to see if it's positive or negative. So if you chose the x value to be 0, okay, we could literally plug in 0 here and 0 here, but notice how we would also need the y-coordinate. Do you know the y-coordinate when the x-coordinate's 0? No, because this is the only coordinate they gave you, right? So in this case, the sign chart method fails you because you don't have enough information to test to see if the first derivative is positive or negative. Notice how you need an x and a y in this case. So if the sign chart isn't going to do you any good, let's try the second derivative test. So if this is the first derivative, I'll get rid of the zeros, can we figure out the second derivative? Yeah, by doing what? Implicit, because we have x's and y's mixed in, and a quotient rule, because it's a fraction. So we'll have low d high 6y dy over dx, and then we'd have minus 1. Low d high minus high d low. Every time you take the derivative of a y, you got to write dy over dx. All over bottom squared. Don't clean it up, because that would just give you a headache. If that's the second derivative, where can we go from there? Plug in your critical point, okay? So we'll have 3 plus 1 squared, that would be 4. And then we need 6 times 1. What about this derivative part? If plug in 0, right? If you were to plug this point into the derivative, okay, notice how we already did that, we would get 0. So 6 times 1 times 0 is 0, minus 1, negative 1. Then we'd have 3 times 1 squared minus 1, which would be 2. In the next parenthesis, 1 plus 2 times 1 times another 0. So we'd just be left with 1 there. All over 3 plus 1 squared, which would be 4, and then you got to square that. 16. Negative 4 minus 2, negative 6. All right, is our point a max, a min, or neither? 3, 1 is a max because the second derivative. Go to Noosh. The second, there you go. Second derivative at 3, 1 is negative. Okay, so we confirmed that we have a critical point. Okay, we have to test that first. We have to make sure that it's a possible max or min. And then we can do the second derivative test to see the concavity to confirm max or min. Do you see how this was our only option? Okay, the sign chart failed us because we didn't have enough information to plug in for the first derivative. We're okay? We're good? All right. All right, so last night I asked you to just look at page 253 because we're going to start to look at these connections a little bit more just for practice, getting used to all the relationships. And the first graph that we did was the original graph of f, and we wrote down a bunch of different things for f prime and f double prime. So based off the responses from the Google form, most of us said we just wanted more practice, but we're having a little trouble kind of keeping everything in line because there is a lot to take in. I understand that. Some of us said we're not quite sure what to look for. Do we look for increasing and decreasing? Do we look for maxes and mins? Do we look for above x-axis, below x-axis? Because there's a lot of things going on here. So what I wanted to do, based off of your responses, is try to bring everything together for you on this worksheet. So kind of a go-to page that you should have got when you came in. Do we have this? Okay. We're going to fill this out before we try some of the other examples, because maybe this will help us with the other ones. Okay. So we're going to try to have a nice formal chart here relating f, f prime, f double prime, and maybe if some of the characteristics are on the x-axis, above the x-axis, or below, meaning 0, positive, or negative. Kaden, I think it's underneath your binder.
Is it?
Yeah.
That makes more sense.
All right. Let's go ahead. Let's first kind of discuss what these different functions mean. So when I say f of x, what does that also represent in terms of a graph? Yeah?
Y.
The y value, or the original function value. Okay, so this is a y value of the function. You might have to write a little tiny. I'm sorry if the boxes are a little squished. I just tried to fit everything on one page. All right. So then the first derivative of f represents what? The slope. Okay. So we'll say slope of f. Okay. And if you're analyzing the slope, you're essentially analyzing how the y values are changing. Are the y values increasing? Are the y values decreasing? So we'll say how y values change. What does the second derivative tell us? Either related to the first derivative or the original, however you want to approach it. Good, Kaden?
Concavity.
Concavity. Okay, so concavity of what function? concavity of f prime, concavity of f. Okay, so the second derivative is basically telling us how the slopes change. You see how we just take the previous function meaning and we're applying a change to it? Are the slopes increasing or the slopes decreasing? So if the second derivative tells us concavity of f, can we think about what it would tell us about f prime? Yeah, the slope. If the first derivative is the slope of the original, notice how the second derivative is the slope of the first derivative, because you just add an extra prime mark in there. Okay, an extra derivative, an extra slope. All right, so let's think about this. If the y value of a function is 0, what does that mean about our graph? It's on the x-axis. Okay, so you have an x-intercept. If the derivative or slope value is 0, what does that tell us? Yeah?
Extrema.
Extrema, critical point. Yep, possible max or min. Critical point of f, okay, the original function. What if the second derivative is 0? What does that mean for f, or what does that mean for... Not, it begins with an I, not implicit. Yeah? Inflection. Okay? So, we'll say possible. Okay? Possible inflection point of f. Okay, the original function. If the second derivative is 0, what might that tell us about the first derivative? Whatever connection we put between these two, the same connection should be found between these two. Because we have an original function first derivative, and this is essentially original function and first derivative, if you were to take away a prime mark. Yeah?
That is showing like possible maxes or mins of that time.
Critical points. Okay, so this would be a critical point of f prime. Okay, the derivative, where the derivative has a max or a min. Now, since these are potential maxes and mins and potential inflection points, you'd have to check sign changes, like positive or negative. I think that kind of goes along with these descriptions, but we're heading in a good spot. Okay, so if you can identify the relationship between f and f prime, the same relationship holds true for the first derivative and the second derivative, related to each other that way. All right, what if f is positive, if the y value is positive? Above x-axis. What if the first derivative is positive? F is increasing. What if the second derivative is positive? Good, Anush?
F is concave up.
F is concave up. All right. What if the second derivative is positive? What does that tell us about the first derivative? Yeah?
It is increasing.
It's increasing. All right, and the last one. If the y value is negative, we are below the x-axis. If the first derivative is negative, we know f is decreasing. If the second derivative is negative, the original is concave down. But we also know that the first derivative is decreasing. Okay, the slopes are decreasing. Remember those three examples I went over? Like slope of 1, slope of 1, slope of 1, and if they increase and decrease. If the slopes are decreasing, you're creating that concave down kind of path to it. okay? So I'm hoping this chart helps us, kind of a go-to relationship for all these different properties. Let's see if we can apply them to just some of these examples. So we're going to use this same graph for every single one. It just depends on what it represents. So for instance, for number 1 here, we're going to let this graph represent the original function. Okay, so we're going to take a look at kind of this information for f, perhaps. So where is f decreasing and concave down? If you were to trace it, maybe we can label the decreasing sections. But of those 2 sections, can we also describe where we're concave down? We're kind of an upside down parabola shape. What do you think, Anuj?
Like from 2 to 3?
Okay, so from here to here, notice how we're concave down. We have that upside down parabola shape. But then after that, we look like a regular parabola. So 2 to 3, definitely. Is there another interval on this first piece where we're decreasing? But also concave down? Yeah.
Is it -7 and -5?
-7 and -5. Yep, there's that same kind of upside down parabola shape. Looks good. All right, where is f increasing and concave down? All right, so let's label the increasing sections. Yeah? -1 to 2. So this piece here, definitely concave down. I like it. All right, this printed as B, but it should be C. At what values do we have inflection points? So where the concavity changes. Definitely. Okay. Oh, yeah? Good. Look at that. All right. So sometimes it'll help if you exaggerate the curve. So concave down, concave up, concave down, concave up. So -5, -1, and 3. Definitely. All right. We're going to add in part D over here in the corner. Where is f prime, okay, the first derivative, undefined? And then we'll justify our answers. If this is the original graph, then f prime would be the slope of this graph. So where's the slope undefined? What do you think, Anuj?
3.
Because?
There's a vertical tangent.
Vertical tangent. Definitely. Okay, slope is undefined. It's a vertical line. Any other spots? You want to keep going, Anuj?
-7 and 7.
Because?
Yeah, those endpoints.
Endpoints. Remember we talked about vertical slopes, endpoints, and sharp points or cusps, however you want to phrase it or remember it. Perfect. Okay, so that's all information assuming that this graph is the original function. Let's try 2. Now we're going to assume that it's a derivative function. So look at your table. We're kind of going to be utilizing the middle piece. All right, where is the original function increasing? What do you think, Christian?
The positive y values. So
Okay.
x from -7 to -5.
Yep.
-1 to 2.
Yep.
Wait, not the 2, not the 2.
Mm-hmm.
-1 to 5,
Yep.
and then 5 to rest it.
7, and you said because the positive y value, so f prime is positive. Good. All right. Where does the original function have a min? Go, Caden.
-1.
Because?
Because it changes signs from negative to positive.
You said it. Because
Graph.
the graph of
F prime.
f prime. Okay, because f prime changes negative to positive. All right, where is f of x concave up? Got a Anuj?
From -3 to 2,
Uh-huh.
and from 5 to 7.
Because
F of x is increasing.
f prime
Oh yeah, f prime of x is increasing.
is increasing. Good. Okay, notice how based off our table, if we wanted f to be concave up, that also means f prime is increasing. Okay, the slopes are growing. So -3 to 2, and then 5 to 7. Good. All right, at which values of x would we have, or a point of inflection on the original graph, the original function? Yeah?
Would be -3, 2, and 5.
Why? Good.
Because it goes from decreasing, increasing, increasing, decreasing.
You said it. Because?
F prime of x.
Uh-huh. Because f prime of x changes, let's see, if you're changing increasing to decreasing or decreasing to increasing, what are you actually creating? If you're changing decreasing to increasing, increasing to you're creating a max or a min. So that might be a little less wordy.
Yeah.
Okay, so f of x, because f prime has a max / min. Good. Are we doing okay? Does this table help a little bit? Okay. I hope. All right. Last one. Let the graph represent the second derivative this time. Where is f of x concave down? We want the second derivative to be negative. Okay, so if we're assuming that this is the graph of the second derivative, where are we negative? There we go. Because f double prime is negative. Where is the first derivative decreasing? Yeah?
-5 to 1.
Yeah. Because?
That is the second derivative. F double prime.
Mhm. Is negative. It's the same reasoning, okay? So if the second derivative is negative, we know the original function is concave down, but also if the second derivative is negative, which is the slope of the first derivative, that means the first derivative would be decreasing. And you can see that based off our table. F is concave down, f prime is decreasing. Okay, same justification for the negative location of the graph, at least. All right, and last one. At which values does f have a point of inflection? What do you think, Anuj?
-5, -1, and 5.
Because?
F double prime has a 0.
And?
And there's a sign change.
And there's a sign change. So I think we might have to go back and
Not 5.
not 5, okay? All right, looks good, guys. I bless you. I think we're going to stop there for today, and we'll go ahead and save the other two graphs I want to check out for tomorrow. And please, if you have a calculator, can you bring it tomorrow? Because we're going to do a few example problems utilizing that.
I'm putting this right up through the front.
Right now, freaking.